Good morning, class. We are looking at chapter 2, limits 2.5, continuity. We've looked at limits of sequences, limits of functions at infinity, limits of functions at finite numbers, algebraic method, and now continuity. So recall limits of functions at finite numbers, finding limits by numerical and graphical methods. This is read the limit of f of x as x approaches a equals L. The limit of a sub n as n approaches infinity is equal to L. We say a sub n converges to L. This is about sequences we studied. The limit of a sub n as n approaches infinity is either infinity, negative infinity, or does not exist. The sequence diverges. To find limits, simply plug in and observe. If we look at all of these graphs, we are interested in finding this limit. As we approach a from the left and right in all cases, so we use this branch and this branch from the left and from the right, and then from the, as far as the y coordinate is concerned, we are approaching L, and in all cases, the limit of f of x as x approaches a exists, and it's equal to L. In this case, f of a is also equal to L, which makes it continuous. In this case, f of a is something else. In this case, it's b, and it makes it discontinuous. And in this case, we don't even know what that is, makes it undefined. Horizontal asymptote, the limit of f of x as x approaches negative or positive infinity is equal to L, gives rise to the equation of a line y equals L as horizontal asymptote, or HA for short. Limit of f of x as x approaches a, or a from the left or right, is negative or positive infinity. It gives us vertical asymptote x equals a. One-sided limits, a function has a limit at a if limit of f of x as x approaches a from the left and a from the right are the same. They are both equal to L. And now section 2.5, continuity. Here's the definition. A function f is continuous at x equals a if, here's the definition of a continuity, if the limit of f of x as x approaches a equals f of a. We've discussed that. So what does it mean? Number one, f of x exists. The output at a does exist. Number two, the limit of f of x as x approaches a exists, and it equals to L. Number three, the limit of f of x as x approaches a equals f of a. The limit is the same as the output. That's exactly what we say here, that has those three parts. A function is continuous over an interval I if it is continuous at each point a in I. If f is not continuous at x equals a, we say that f is discontinuous or has discontinuity at x equals a. Direct substitution property, reminding you a continuous function at a has the following limit value, the limit of f of x as x approaches a equals f of a. Functions with the direct substitution property are called continuous at a. That's the synopsis of the section. And let's get started with this simple example. And reminding you about one-sided limit, reminding you of the limit of f of x as x approaches a equals f of a, that indicates the function is continuous. So at which numbers is f of x discontinuous and why? Well, let's figure out the numbers. Obviously, at 1, at 3, at 5. Now, why? Let's look at each case. Let's start with 1. What's going on with 1? With 1, we don't know what's f of 1. We don't have a solid point, so f of 1 is not defined. But the limit exists. So if you approach 1 from the left and right, from the left we are going this way, from the right we are going this way, we are moving towards this hole, and the limit of f of x as x approaches 1 does exist, and it's equal to this y coordinate, which happened to be 1 as well. Let's look at the next one, number 3. What's going on with number 3? Number 3, limit of f of x as x approaches 3 does not exist. Why is that? Well, let's look at the limit of f of x as x approaches 3 from the left and 3 from the right. Here's number 3. From the left, we are going this way. From the left, we are going this way. We are in this branch, and the answer is -1 here. From the right, we are going this way. We are moving towards this hole, and the answer is 2 here. One-sided limits are different. The limit does not exist. What about f of 3? You look at number 3, you look for a solid point. And this is the solid point with y coordinate -1. So that's -1. So we could figure all of them out. And by the way, this is considered continuous at -1 from the left, but nevertheless, it's continuous at number 3 from the left, but nevertheless, it's discontinuous at x equals 3. Finally, what about 5? Let's look at the fact that the limit of f of x as x approaches 5 is not equal to 5. So the limit of f of x as x approaches 5 means on the left we are moving this way. Let me just, so we are moving this way from the left. Also from the right, we are moving towards the same point. And the limit does exist and seems to be equal to 1, this y coordinate. So this seems to be 1. Whereas f of 5, you look for the solid point, seems to be number 3. So they are different. G of x is a piecewise defined function, 1/2 x plus 3 for x less than -2, x minus 1 for x larger than or equal to -2. And again, definition of a continuity and one-sided. Is g of x continuous at x equals -2? Why or why not? First, it's important to know why we are interested in -2, because each piece is a linear function, is a line. In other words, the top piece is y equals 1/2 x plus 3. Let's just write that. So this would be the line y equals 1/2 x plus 3, which is continuous from negative to positive infinity. Therefore, it's continuous from -2, from negative infinity to -2 because of the limitation that they put here, okay? And this one has the equation, let's say y equals x minus 1. Again, a linear function. that is continuous from negative to positive infinity, therefore it's continuous from negative to infinity. So we have to check the end point. That's the idea. Okay. And so there are three things we're going to look at. We're going to look at the functional value and the limit from the left and right. That makes it 3. So the functional value means G, let me erase my word. That means G at x equals negative 2. So I have to look at the equality. I'm going to use the bottom piece. You plug in negative 2 and you get negative 3. So that means G of minus 2 is given and it's equal to negative 3. Then I look at the one-sided limit. I start with the left side. And the left side, I have to go with the less than, and I have to use this piece. So I use half of x plus 3, and I plug in negative 2. So when I plug in negative 2, I get negative 1. Plus 3, I get positive 2. I also look at the right side limit. By that, we need to look at x larger than negative 2, which means I have to use the second piece. And if I plug in negative 2 here, the answer is negative 3. So clearly, the limit from the left and right, they are not equal. Therefore, the limit of g of x as x approaches negative 2 dne does not exist. And therefore, the function is not continuous at x equals negative 2. So that's the final answer as far as the question is concerned. However, if we want to add something, how about this question? Is g of x continuous at x equals minus 2 from the right? Okay, so if you look at the functional value, you get negative 3. If you look at the right side limit, you also get negative 3. Because these two are the same, the answer is yes. And that's important to understand, everybody. Why the answer is yes? Because the functional value is identical to the right side limit. That's the idea. Very straightforward. Types of discontinuities. We clearly see a hole here, we see a hole here, and we see a dot. There's a difference between the two functions. Nevertheless, both of them are discontinuous. Parts A and C, it's called removable discontinuities. We could remove the discontinuity by redefining f of x at just the single number 2. Notice what's happening with this one. This is just a rational function. This is the same rational function when x is not equal to 2, because remember, the denominator can't be 2. So even if they don't mention it here, we should know that's the case. And so at x can't be 2. Okay, end of this story. But when we add this piece means we do have a functional value at 2. So that really refers to this pair having coordinates 2, 1 from here. So I want to make sure we understand what happens here. So both of these functions are discontinuous. There's a hole. So if you simplify this by factoring the common factor of x minus 12, please understand, in this case, x equals 2 is not a vertical asymptote, because if you recall when we did graph rational functions, we have to put it in lowest term first. So what makes the denominator 0? In this case, 2 creates a hole. In fact, this hole has the coordinates 2, and then if you plug in 2 in here, 3. So you know that's the hole. So the function, let's say g of x equals x plus 1 is a line and it's continuous. So the line without a hole, the line, if we didn't have a hole, would be this. Now the hole is this rational number. So the difference between these two is that because we have a denominator x minus 2, there is a hole. And of course, how do you fix it? In this case, it has been defined at 2. You have to define it at 3 to fix it. So that's called removable because it can be fixed. However, if we look at this case, or this case, none of them we can fix. This one is the infinite discontinuity, also known as vertical asymptote. This one, jump discontinuities. You have a bunch of them. There's a jump. So we can't do anything about it, but this, we can fix it. Is h of x continuous at x equals 3? Where h of x is a piecewise defined function, x squared minus 9 over x minus 3. Of course, x can't be 3. And we are defining it h of 3 to be 7. That's the meaning of that. When you write, when you have this bottom piece, means h of 3 is 7. That's the meaning of it. So there are two things we want to look at. We want to look at the limit and we want to look at the functional value. The functional value is given. The limit, you have to take the limit of this piece because it says when x is not equal to 3, we have this one. So take a limit as h approaches 3. So if you plug in 3, of course, you get 0 over 0. And that is indeterminate. And the technique we have discussed is factoring. The numerator is x squared minus 9, which is 3 squared. So x minus 3x plus 3. Common factor of x minus 3 is dropped. Limit of x plus 3 as x approaches 3, plug in. And the limit is equal to 6. So the limit exists. However, this means h of 3 is 7. Are they equal? The answer is no. Because the limit of h of x as x approaches 3 equals 6, not equal to the functional value h of 3 equals 7, then h of x is discontinuous at x equals 3. So can you fix it? You can redefine the functional value. If you redefine it as 6, you can fix it. Now, again, reminding you of what we did previously with the algebraic method. We want to take the limit, and as always, you plug in and you observe. So if I plug in 6 here, 6 minus 6, they cancel each other. This is 0, square root of 0 is 0, so we get 3. This is 6 squared, 36, minus 7 times 6, 42, plus 12. So the numerator is 3. 36 minus 42 plus 12 is 6. And the answer is 1/2. In other words, you plug in, it works out, you're done. The limit of 1/3 minus 1 over x minus 3 as x approaches 3, you plug in You get 0 over 0. It's indeterminate. You're dealing with a complex fraction. So you use LCD. LCD is 3x. You're going to multiply the top and the bottom by that. Again, as x approaches 3, x minus 3 becomes 0. So you never, ever distribute. It's the product of the two. You multiply these two, you get x. You multiply these two, you get negative 3. And you drop the common factor. If you plug in, you get 1 over 9 as the final answer. It's just to remind you of a couple of examples and what we did previously. Algebraic method. Example 6. At what point or points is f of x discontinuous? Name the discontinuity. If removable, how would you redefine to remove it and fix it in essence? So first, quickly, what are the points? So we start from the left and we go to the right. The very first number we see is negative 2. The next one, there's a hole here, negative 0.5. The next one is here to here. There's a jump 0, jump 1, vertical asymptote or infinite limit 3, and there's another hole here, 5. So those are the numbers we notice immediately. Now let's look at cases and call them out. First, we notice that at 0, it jumps. At 1, also it jumps. So 0 and 1, those are jump infinity. We also notice number 3, we have a vertical asymptote or infinite limit. Then the rest of them, negative 2, negative 0.5, and 5, they are all removable. So if they're removable, how do we fix them? The removable ones can be fixed by redefining them. So the question is, how do you redefine them? Let's start from the left to right, and let's look at negative 2. As we approach negative 2 from the left and right here, left is moving towards this point, right is moving towards the same point, and as you can see, the limit exists. The limit of f of x as x approaches negative 2 is 2. Therefore, we don't have f of negative 2. We redefine f of minus 2 as the limit, 2. So f of minus 2 equals 2 will fix the problem. All right. Now we go to the next number, negative 0.5 here. As you notice, here's number negative 0.5. From the left and right, we are moving towards this point. And that seems to be about 3.5, which means the limit of f of x as x approaches negative 0.5 must be 3.5. However, the functional value is 1. You redefine as f of negative 0.5 instead of 1, the value of the limit 3.5. Last one is number 5. We approach 5 from the left and right. We approach this hole from left and right. And as we look at this hole, we notice the y coordinate is 5. So the limit of f of x as x approaches 5 is 5. So we are going to redefine this in the following manner. F of 5 also must be equal to the limit 5. And if we do so, we have removed the discontinuities that are removable.